Yeah, okay, now let's go into chapter 3.3, retaining structures. This will be the wrap for your chapter 3, alright? So first and foremost, let's look at the common types of retaining structures that we have in the market. Sometimes they're also called retaining walls, also that they refer to the same thing, right? So the most common type is probably the gravity walls. You can see these are the cross sections, and normally it's trapezoidal in shape. As you can see here, the back is normally vertical. It could be inclined if you so need it, and there's a name tells the wall gains its stability and load resistance capacity from its own weight, right, by gravity. And the second type is the cantilever wall, similar to the gravity wall, but you can see it's a lot more slender and slimmer, alright? And because it's slenderer and slimmer, it could go higher. Alright, this could go up to 10 meters and more if you want to, and can see that at the bottom of it, the base is long, right? The base that retains the soil, where the soil sits on it, this part is long. Right? And the third type is the counterfort wall. You can see it's similar to the cantilever wall, just that at the back of it you have extra support, which is known as a counterforts. It's alright, we'll see some details after this. And the fourth type is very popular in Malaysia, especially in constructing the flyovers. These are called the reinforced earth wall. We'll see again from the picture how they look like. You will recognize this easily. Alright? Okay, these are the counterforts. As you can see, it's essentially a cantilever wall, but it has a counterfort at the back, and this is how they look like, how huge and how tall they are. These are the workers, right? They are being backfilled with the soil eventually as a retaining structure. And the tie stems, these are okay, the vertical bit is the stem and the base is a slab. And this counterfort actually tie the stem to the toe, and this helps to reduce the shear forces that's acting on both the stem and also the base. So imagine without the counterfort, this wall could not have gone too high up, right? Otherwise it would have toppled, or the moment would be too great for the wall to take. And this is an interesting one. They are called the buttress walls. These are not very common now today. If you look carefully, they are almost like the opposite of the counterfort walls, where you have this extra support on the outside of the wall. They are called the buttresses. And you see, they're on the outside. So yes, example that we are having here is actually one that is a dam, alright, for impounding the water. And this is an old fortress, as you can see, overgrown with vegetation and all. We call them the transverse supports, the other way around, terbalik lah, right, on the outside. Again, it ties your stem to your base, and this buttress is actually a compression member. It makes sense, right? Look here. This is a wall with a stem. These are the buttresses. The water is pushing the wall, exerting a pressure, so the wall will push it against your buttresses. That's why these are all compression members, because they are being placed outside the wall. Right? As I said, these are not very common today because they are taking up too much of space on the outside, right? As you can see here. And for aesthetic value, some people may not think this is very beautiful, maybe. Okay. Next, this is the reinforced earth wall, right? As I said, this is very common in Malaysia in constructing our highways. It is actually a composite material. Why? Because you lay these steel strips, alright, steel strips in the ground, and then you pour your earth in, right, dump the earth, and you compact them. And layer by layer, once you put the strips in, you put the layer of soil, you start to compact it. Then you put in another layer of reinforcement and you compact it. So layer by layer, eventually you get the height that you want. And these strips are tied to the fronting panel or the facing panels, as you can see here. And these are the ones that you see from the outside. Say this is a flyover, you drive along here. These are the panels, these are the walls that you see. I think you can remember now, in Malaysia, the common ones are actually hexagonal in shape, and at certain intervals you see JKR written on it, right? So this is what I meant by the reinforced earth walls that are very commonly used in Malaysia for flyover constructions, alright? And the way it functions is that normally we pop in quite sandy soil, alright? Laterite is the most common because we have plenty of those in Malaysia, and the friction between the soil and your strips, the reinforcement elements, will actually provide tension to the embankment or the raised ground being contained by your walls. So this will actually kind of produce a kind of cohesion to the soil. but really the soil is not clay, alright? It could be a sandy clay, and most likely it's going to be a granular soil like sand for backfill and for good friction. Okay. Right. The next common one that you see is a gabion wall. So essentially it's a partially flexible block construction where you have a metal cage. Usually it is made of steel wires coated so that it can withstand the weather, and inside we'll just pop in the rocks if you like, and sometimes they are built angled. This is vertical, but sometimes they are built angled so they can have a better stability. If they are not angled, as in this case, you can see that they are at the top is actually a rubber wall, at the bottom they put in the gabion wall. Just take note of this. You could see that there is on this part of the wall, which is not the gabion actually, it is the part of the rubber wall. There are these whip holes. I just wanted to show you this because later on we are going to talk a little bit more in details about whip holes. Alright? Okay, and you can guess why the whip holes are there: to drain out water from the back of the wall, to make sure that the water doesn't accumulate from the back. Because once you have accumulated groundwater at the back or pour water at the back of the wall, that is going to exert an extra pressure, the hydrostatic pressure onto the wall, which we'll try to avoid. Alright? Okay. Next, the sheet pile wall. Again, these are very common. You have seen these quite commonly along river banks, right? And sometimes in deep excavations. Alright, so what are they actually? They are just sections of steel or timber. Again, today we rarely use timber because of for sustainability issues and such things, and they are intertwined or connected. Look at the section of it. 1, 2. So this is the bit where they are connected. In reality, this is where they are, and they are pretty watertight to a certain extent. Alright, and usually, as I said, we use it for waterfront structures. As you can see, riverbank. We also use it for deep excavation in this situation, as you can see. And they could be permanent, it could be left there for forever, or it could be just for excavation. Once it's done, they put in the formwork, cast in the concrete walls, they were taken in out. And for deep excavation, normally we put in struts as well. We have these supporting struts cutting across the excavation site, and you have corner struts as well. Why? To make sure that the wall doesn't cave in. Alright, what did we say? It is flexible, hence you got to take care of it, alright, by putting in the struts. Okay, and next, this slide is showing us some failures that you could encounter for your building structures. And yes, you are right, these partially, it could be lateral forces pushing the wall to come off, like in this case, because your top is doing that. In this case, it looks like a slope failure. Alright, so it really depends on the situation, and sometimes it could be a combination of both a failure of the wall and failure of the slope. Alright. Okay, when we analyze retaining walls or retaining structures, we'll look at them in terms of two categories. First is the stability failure, which is looking at the wall as a whole. So you could have a problem of overturning, as you can see here, overturning at a certain point. So this is obviously a moment problem, right? The wall is not breaking up or anything. It's just the whole body of the wall is toppling over, and it has a certain point here. So, and the second one is sliding. This is like in mathematics we learn is translational movement, right? From one point it moves to the other. Okay. In this case, it's moving to the front because it's trying to retain the soil at the back, and this soil is pushing it forward because the wall is not quite sufficient in terms of load resistance capacity to resist the forces coming in from the back. And the third type of stability failure that we can encounter is the bearing failure. Probably this is the most common, where the foundation, if you like, is not quite sufficient to take the vertical load coming down from the wall itself, and also the soil that it is trying to retain. Alright, there's just three: overturning, sliding, and bearing failure. And you will recall that these stability analyses are similar to the ones that we discussed before for your foundation before this in 3.1. Okay, and the second category of failures that we're looking at are the structural ones. Structural means it is the element that you pop into the ground. So the wall, which is reinforced concrete in this case. You could have stem failure, as you can see here. The stem is failing, or you could have heel failure, or you can have toe failure. So by now you have noticed that yes, the one that is in the bit that is in the retained soil is the heel. The bit that is jutting out is your toe. So it's like your foot, right? This is your toe and this is your heel. And the last one, is the key failure. Now, the key that we're referring to here is the shear key. Alright, kunci Ricci. If I were to ask you, is the shear key good or bad for the stability of the wall? And obviously, it's put in there to enhance the resistance of the wall. Why? The longer it is, the greater passive pressure that you can get from the front to resist the wall from overtopping. Alright? Now, we go through some of these, the design criteria again. For bearing capacity failure, we are looking at the loads coming down, then the foundation of the wall, which is the base of it, should be able to sustain the load. And the rule is that you got to make sure that the resultant, the vertical and horizontal forces, that is the vector of it, must fall within the middle third of the base. No need to cry over this. We're going to look at the formula, and you can understand it quite easily after this. Okay, just bear in mind the resultant force coming through on the base should not be outside the middle third of the base. And for settlement, there cannot be excessive settlement. The same criteria for your shallow foundation. As for sliding, these are the formulas that you can use. It depends on which one, safety factor you want. If it's 1.5, this is the formula that you use. If you are talking about 2. You want a safety factor that is higher, then you could be using this. It's a very straightforward thing. Alright. In terms of overturning, you got to make sure that your resisting moment against your overturning moment is greater than 1.5, meaning that it's 1.5 times greater than the moment that is pushing the wall over. Alright. For backfill soils, discussed before, as similar for the reinforced soil, you wouldn't want to pop clay in. You want to put something that's granular for the friction. And number two, it's a lot more difficult to transport and to compact clay compared to sand. Alright, so usually it is coarse grain soil that we want. Okay. And we did talk about drainage. Remember the whip holes? Yeah. So the most common ones are the whip holes. So this is the wall. It is retaining the soil at the back. So there are these whip holes that what we see is from the front here. There are little holes with pipes. Actually, it goes through the wall, and at the back, before in the interface with the backfill soil, is actually some filter material. Remember, we talked about filter material in the previous subtopic on earth dams. They are simply another layer of soil or granular soil, more specific, that is to help to make sure that the water could flow through, but it's not so fine that the water is going to bring the material out and cause piping in the ground at the back. Alright, and the second type are the back drains. You can see it covers the back of the wall, and there's a collection point at the bottom here to drain out the water out of the wall. And the third type are the inclined ones. This is a bit similar to the chimney drains that we see for earth dams. It intercepts the flow by being placed in a slanting position. So water coming through, rain, runoff, seeps into the ground, comes through here, can't push the wall because it will go into the drain and be taken out. Alright? Okay. Now, we'll just pause a bit before we go in to look at the subsequent design process. How do we dimension out the wall, and so on and so forth. Alright, pause for a bit.